It's Chris again. In my last video, I showed how to make the significand multiplier at the heart of the floating point multiply circuit even faster by using 3-2 compression to reduce the penalty of propagating the carry bit during addition. This video is going to be about perspective, what we've done so far, trade-offs where we could have done things differently, and what is left to be done. I started with building a parameterized module which can be used to classify any IEEE 754 binary 16, 32, 64, or 128-bit datum as a nan, infinity, 0, a subnormal number, or a normal number. I then presented a parameterized version of the floating point multiply circuit which can handle any of the IEEE binary floating point formats. I spent time testing these modules, and perhaps that's a good place to start the discussion of technical details. You might have noticed that when I tested the multiply circuit, I really spent most of my effort testing the exponent field of the floating point numbers and very little time testing the multiplication of the significand field. At least that's the impression the videos may have given. In fact, I spent a lot of time verifying the correctness of the significand multiply logic. When I started this project informally several years ago, I speculated that the slowest part of the circuit was going to be the significand multiply module. So even before I learned Verilog, I was spending time thinking about how to make that portion of the circuit as fast as possible. It was at that stage that I recognized how I could use parallelism to accelerate its performance. When I did finally learn Verilog, the significand multiplication logic was the first part of the circuit which I implemented. Also, because multiplying two 11-bit quantities can be tested exhaustively, I literally tested every possible pair of 11-bit input values. So, when it came time to test the whole floating point multiply circuit, I didn't think it was necessary to spend much more effort on that part of the testing. Up to a point, I still think this way, but here's the rub. I've tested every possible pair of significand values for the binary 16 format. I've done a limited amount of testing of the multiplication of the significand values for the binary 32 format. To exhaustively test every possible pair of 24-bit input values requires over 70 trillion tests. That's 2 to the 46th power unique tests because we know that the most significant bit of both significands will always be 1. For one version of the binary 32 significand multiplier, I have actually performed that test using an FPGA. I was able to test 100 million cases a second, and it still took over 8 days for the test to complete. I can't be bothered to calculate how long it would take to exhaustively test the significand multiply units for the binary 64 and binary 128 formats. I need a practical way to perform the tests. This means I need to learn formal verification techniques before I can have total confidence in my significand multiply modules for 64 and 128 bits. This is something I will have to tackle later. And this brings me to the next point. When I started hand optimizing the significand multiplication code, the Verilog code lost its generality. That is, before I started using parallelism to accelerate the significand multiplication module, I had already used two other strategies for multiplying the significands. The first was to use the Verilog compiler to create the circuit for me. The other was to build a relatively simple and slow version of the significand multiply module. These two methods of multiplying significands shared the strength that the Verilog code was fully parameterized, and simply by changing the NEXP and NSIG values, the module could be recompiled to support all four IEEE binary floating point formats. When I hand optimized the significand multiplication code, the multiplication module became specific to a particular binary floating point format. For simplicity's sake, I wrote the hand-optimized code only for the binary 16 format. If I was writing C code, I could use conditional compilation to control which of the type-specific significand multiplication modules was used. I would modify the fpmul.v code as follows. As you can see, the Verilog code has been modified to use the hand-optimized significand multiplication logic for the binary 16 data type, but relies on the Verilog compiler to generate code for the other IEEE binary floating point formats. As new modules are written for the other binary floating point formats, #lf clauses could be added. For example, this version of the code uses type-specific significand multiply logic for the binary 16 and binary 32 formats, but still relies on the Verilog compiler to generate the significand multiply logic for the binary 64 and binary 128 formats. Like C, Verilog supports conditional compilation. Unfortunately, Verilog's conditional compilation doesn't seem to be nearly as flexible as C's. Verilog supports if-def and if-ndef, but it doesn't allow the testing of the value of a defined macro. So I can do this, but I can't do this. If any of you who are more expert in the use of Verilog have a solution to this problem, please let me know.
While I'm talking about the hand-optimized significand multiply module, now might be a good time to discuss just how much performance was gained. The slowest path through the FPMul circuit using my generic significand multiply module took just over 35 nanoseconds. When I rewrote the module to exploit parallelism and use a carry look-ahead adder, the slowest path through the FPMul circuit took just over 27 nanoseconds. My final optimized version of the module took just over 25 nanoseconds. Then the question is, so how does this compare with letting the Verilog compiler implement the significand multiplication circuit itself? Fair question. If you have watched the YouTube video of Matt Godbolt's talk titled, "What Has My Compiler Done For Me Lately?", the results of my hand optimizations compared to the circuit produced by Verilog will be no surprise. The code using the Verilog compiler generated significand multiply logic was just over 25 nanoseconds, which is slightly better than the best result I could produce by hand. By the way, a link to the video of Mr. Godbolt's talk should be appearing on your screen now if you're interested. To be fair, comparing the Verilog generated significand multiply performance to my handwritten multiply circuit is comparing apples to oranges. For the gory details, one has to be acquainted with the specifics of FPGA architecture. In particular, the Verilog compiler is exploiting math resources which I can't access directly using generic Verilog code. The code I've written is using generic FPGA lookup tables scattered about the chip to compete with a tiny logic element on the FPGA specifically designed to perform mathematical operations especially fast. I'm actually proud of the fact that my hand-tuned algorithm came so close to a custom-built math unit. My performance was within a fraction of a nanosecond of the performance of the special hardware. The math-specific circuitry on the FPGA doesn't just have more speed than my handcrafted code. It also takes up fewer resources, leaving more of the FPGA free for other functionality. Now, it would be fair to ask me if I consider my hand optimization experiments a failure. For me, no. One of my goals in this project was to learn how to make the circuit fast, and as I've stated before, when I allow the Verilog compiler to implement the significand multiplication logic, it generates a black box. That is, I get no visibility into how to make the circuit fast. That I was able to use generic Verilog code to come close to the performance of a task-specific logic block on the FPGA tells me I've learned a lot about how to make the circuit fast. There's another aspect of comparing my handcrafted Verilog code to the performance of a specialized FPGA logic block. It's a little like saying that programmers are wasting their time learning how to write assembly language code because the compiler will almost always do a better job. Even if that's true, without an understanding of assembly language, compiler writers can't write good compilers. The fact that I now understand what kind of tools I can exploit to make a math unit faster means that now I'm more capable of designing a math block should I ever have a need to do so. Things which I have left undone so far: rounding the product and replacing the rest of the integer arithmetic and comparison logic. As you may remember, when I computed the product of the significands, I simply truncated the results to 11 bits. The IEEE 754 standard defines several different rounding modes which must be supported. The FPMO module needs to have additional control signals routed into it which specify which rounding mode the programmer wants. And additional logic needs to be added to implement rounding the final result. In the FPMO module, the Verilog compiler is relied upon to generate the arithmetic logic needed to compute the value of the exponent for the product, and to test the exponent to determine if the product is infinity, zero, a subnormal number, or a normal number. Like the code to compute the product of the significands, this top-level code which manipulates the exponents could be rewritten to implement our own gate-level logic to perform each of these computations and comparisons. I'm going to postpone the work of implementing the rounding mode so I can move on to another topic. I will address rounding in a future video. The work of replacing all of the exponent computations and comparisons will be left to the viewer as an exercise. I may eventually undertake the task myself and update the GitHub repositories, but there are so many areas of the FPU which need to be implemented and explained that I wish to address those first. Besides, I've presented enough information in the preceding videos that the viewer should be able to perform this work on his own. Please share this video with friends and colleagues which might have an interest in this video series. Questions and comments are welcome in the comment section. If you found this video useful, please click like below. While you're at it, subscribe to the channel, then click the bell to be notified when new videos are available. Thanks.